going to make a recording on both computers just to see which one works out better. The cost of this is we might waste some wires and switches. And there are a few reasons. So if we design our FPGA that it routes all the signals, say as 16-bit quantities, maybe some of my design logic doesn't actually use 16-bit words or a multiple of 16-bit words. I'm going to waste some of my routing because I can only essentially change routing decisions 16 bits at a time. So there's going to be some waste if I do that. So there have been a few studies that have looked at this over the years. This is one by Yi and Rose from Transactions on VLSI. And what they did is they took a conventional FPGA and they basically changed this routing structure to make some of the wires suitable for routing only multi-bit quantities. Okay, so how did they do that? So what I'm showing here is they take these four wires, okay, C1 through C4, and they're basically going to treat them as a bus. So these are four routing segments that they've built inside the FPGA. And they have some signal coming in from the top here, or some 4-bit signal coming in from the top, and they want to get it into this logic. So they're going to come in from the bottom of the logic block. Let's say their routing algorithm chooses that. All four of these signals, so these are basically maybe bit 0 through bit 3 of some bus, are going to all go left at this switch block. And they have to all go left because while there's a routing mux on every one of these routing wire segments, all four of the routing muxes that I just circled in red would be controlled by the same SRAM cells. So they're all going to make the same decision about is it the wire that comes in from the north that gets switched onto me or not. So we have four sets of switches because we need to drive four distinct wires. But those four switches are controlled by the same SRAM cells. So that's our savings. Instead of every one of the routing muxes that I've circled having its own set of SRAM cells, there's just one set of SRAM cells that's wired to all four of them. So they all make a coupled decision. They all decide that they're going to take the signal from the north and send it out on their output wire. Okay, then we similarly have four routing switches here that are all controlled by the same SRAM cells, and basically decide we're going to each pick the wire, a particular wire, maybe the first wire that each of us is allowed to connect to is going to go into this logic block. So hopefully that makes sense. So it looks like a conventional FPGA, but some of the routing has been replaced with this bus-based routing, where we have to make decisions on, in what I'm showing you, on 4-bit quantities. And those 4-bit quantities will be routed essentially in parallel throughout the island-style FPGA. And then it goes into a logic block that is similarly going to work on 4-bit quantities. Okay, so we're going to take in this data, and it's going to go into 4 separate lookup tables. Okay, so what they found is that they actually get relatively small gains by doing this. They only got a 10% area savings on data path designs. So data path designs means it's not all control logic. There are 16 or 32-bit buses in the designs, and that is the common case. They found that their best architecture used relatively narrow buses. So it's basically what I showed you here. They used actually 4-bit wide buses, which isn't very wide. It's narrower than the usual data types that you're going to use in much of your design. And they found that only 50% of the wires should be bus-based. So they took half the wiring in a routing channel, and they did this trick of grouping it into groups of 4 that all share SRAM cells and make decisions as a unit. And the other half of the routing wires in each channel were conventional. Every routing mux had its own SRAM cells, so it could make its own decision. Okay, so that's the best architecture they found. Pretty narrow bus width, and only half of the routing wires were grouped into these buses. So any ideas why? Why did they get this result? Does this make sense? So they got a relatively small gain, 10% area, and with a relatively not that aggressive use of their idea, right? The buses aren't that wide, and they only made half the wires bus based. So why do you think this happened? It doesn't make sense. So you can feel free to unmute yourself and just chime in, or you can type it into the chat. Yeah, so we still need single bit wires for control signals, etc. So it does make sense that you wouldn't want to make everything bus based. So we are going to need some control signals. There's always a question of what benchmarks they used. Academic benchmarks tend to be a bit older, so they probably didn't have as much logic that is based on buses as the latest designs. The latest FPGAs are very big. More than 1 million lookup tables in state-of-the-art FPGAs. It's difficult to fill 1 million lookup tables with control logic. So what you fill it with is there some control logic, but you tend to have a lot of functional units that are working on 16 or 32-bit data, and then often they're grouped together in SIMD and so on, so the buses get even wider. So their benchmark selection could have affected them some. There will be control logic, but we don't expect, at least in really big designs, that control logic is most of the design. But we certainly need to have some of the wires not be bus-based, because we do expect to have some control logic. So anything else? So control signals is part of it. But still, you might find this result kind of surprising. I mean, I found it surprising, but I do think it makes sense. So once you think about it enough. So anything else that's going to make it difficult for this architecture to get gains? Yeah, so Evan's got a good point. How significant is the CRAM area compared to the MUX area? So they fundamentally can only, they can't save the MUX area with the approach they're taking. So what they're doing is they're taking a bunch of wires, okay, so a regular routing channel, and let's say I did a bus width of 2. So what they're actually doing is they normally you would build a routing MUX, that drives this wire, and you would have configuration cells that control, which input's going to go into it. So maybe it takes its input from there, maybe it takes its input from down there or somewhere else. And what they're doing is basically saying, okay, well, let's think about buses where this guy also could take a signal from, the wire that's above or the wire that's below. And the only thing that they're actually saving, they're not getting rid of the muxes. What they're getting rid of are these CRAM cells. So normally this mux would have its own configuration cells, and they're saying, nope, what we're going to do is we're going to get rid of those, and instead we're just going to wire his configuration to those other SRAM cells. So yeah, so you have to go through and do a bunch of detailed area modeling, and I believe I have this actually on the slide, but the CRAM area is significant, but the MUX area is even bigger. So fundamentally, they're saving some of the area of the routing, but not the bulk of it. So that's going to fundamentally limit how much they can save. And Gil has basically the same thought of like, well, are they saving enough area? Because they still have to have all these routing boxes. So yeah. So another thing, okay, so that's basically, you guys have highlighted this, only saving the SRAMs. So let me erase this so it's not on top of my slide anymore. Another thing that happens is irregularity in the data path. So they have to switch all 4 bits together. And even though you might be doing processing on 16-bit words, for example, you might sometimes have things like sign extension where what you're doing on every single bit is not the same. And anytime you do something different on one bit versus another, it doesn't match this architecture very well, even though you still have buses in your design. So not only do you have to have buses in your design, you have to be doing essentially the same thing on every bit of the data word. Otherwise, you get some irregularity that causes you problems. You really want single bit routing. And then the other thing is that if they use wider buses, so they went with 4 bits, which is relatively narrow. Now you might say, like, most data is more wider than 4 bits, and you're right. But it gets tricky to choose a wider width. If you went to 8 or 16-bit wide data paths, your cost if the person actually does some processing at 6 bits and you have a 16-bit data path, you've wasted a lot of your routing wires. So whenever the architecture bus width that you pre-decided does not match some part of the design, you can waste a lot of routing wires. So that means the gains of going to very wide buses in your routing architecture are kind of outweighed by the risks of you just might waste a lot of them. If somebody uses 20-bit wide data and you built 16-bit wide buses in your routing, you're gonna have to round that up to 32. So that's a pretty big cost. So, so in the end, this doesn't gain that much. Now there are architectures that go further with this concept of bus-based routing. So who's heard of coarse-grained reconfigurable arrays, CG arrays? Okay, so kids heard of it. Okay, so I see a fair number of people have heard of them. So coarse-grained reconfigurable arrays kind of take this idea and go further. They basically and they've had some success, but not as much success as traditional FPGAs. So I don't have time to talk about them a lot in this course, unfortunately. What they do is they go further and basically say, let's try to make most things bus based. So they'll take their logic blocks and instead of building them out of a bunch of LUTs that you can individually program, they'll typically change that to an ALU. Okay, and that ALU maybe that's 16 bits. Okay, so I've decided that I'm really going to be focused on a 16-bit wide data path. And now I'm also going to build 16-bit wide routing channels. So that's basically the same thing that we just did with bus-based routing. Because if I build 16-bit wide uh, data buses in my routing, it does mean I still need 16 routing muxes. You know, I have 16 physical wires, so I still do need at every switch point 16 routing muxes. I don't get rid of those. So I'm back to this problem of only saving configuration RAM. I still need all the muxing that I would normally have had. So what CG arrays usually do is they use very limited routing flexibility. They will not have, they'll try to make the routing muxes quite small. So that makes them more difficult to route. They usually won't have as wide a diversity of, some long wires, some short wires. I can go in make many different routing choices. They try to shrink down the routing muxes as much as they can, which does make them harder to route. But basically, it's because they're trying to deal with, this part of their cost function. That considering your routing to be bus based saves you SRAM, but doesn't actually save you mux area. You still need a routing mux for every bit of the data path. So they got to try to make those routing muxes smaller. So they essentially push down on FS and FC. They try to make those quite small, makes it more difficult to route, but it's in line with what they're trying to do of make the logic blocks smaller by getting rid of all those LUTs and saying we're just going to use ALUs. Can't do as many things as say 16 independent LUTs would do, but it's smaller. Now to get the routing area down, we're going to use bus-based routing, but that's not going to save us enough routing area. So we also have to make our routing relatively inflexible. And so those choices kind of make sense. If you're going to go in this direction to a CGRA, it pushes you towards those choices. I'd say another thing that happens is FPGAs have some CGRA like concepts in them now, like modern FPGAs, because in addition, you can think of the larger blocks, like DSP blocks, RAM blocks, all those hard blocks are essentially coarse grained blocks, bigger things than lookup tables. And if any of you use the cascade chains in the DSP block, or you use the fact that your multipliers can feed an adder inside the DSP block, the DSP block is essentially kind of like a little, very limited CGRA. It uses bus-based routing between things like the multiplies. It might have two multipliers that together can feed an adder. And that's all bus-based, right? These might be 18-bit wide buses. And the number of options of where the inputs to this adder inside the DSP block can come from is very limited, which means the routing muxing inside that DSP block is quite limited. And then I can have a dedicated connection that can feed to the next DSP block, okay, which is a chain connection between the DSP blocks to let me do bigger sequences of multiply accumulate. And again, this might be a 18-bit, or here we're working on the output, so let's make it more realistic. So that might be a 36-bit output. And again, bus based. You either take all 36 of your inputs from the output of this block, or you take none of them. That saves you SRAM cells, and the fact that you only have one choice. You either, if you're going to use this special routing, you either take it from one specific DSP block that maybe is right above you, or you don't use it. Limits the size of your routing muxes. It's got exactly one, either it comes from the regular routing or it comes from this one special spot. So that is essentially a CGRA-like concept. You wind up with your DSP blocks behaving like a more coarse-grained fabric within your fine-grained FPGA. Anyway, any questions on that? It's kind of as far as I'm going to go on CGRAs. CGRAs are actually their own interesting topic. We could spend multiple lectures just talking about CGRAs. If you want to go further on them, they're an interesting topic for a term paper. Okay, so I don't see any questions. So let's move on to a different topic, clocking architecture. So we've talked about how our blocks in an FPGAs work. We talked about how the regular routing works. Let's talk about clocks, because we can't do much if we can't get clocks to all our registers. And FPGAs are kind of tricky because they're so configurable. When we're designing the chip, we don't know which register wants what clock. Okay, so how do we deal with that? Okay, so I'm going to see how skilled I am at breakout rooms. I'm going to try to do a breakout room again. And let's see. That means that I need to remember where the breakout room dialog is. Because I also need to figure out which one of these two sessions is controlling it. Okay, so it's the other computer is controlling it. All right, let's, okay, so we're going to go into breakout rooms. And let me quickly type this in the chat so that you remember what the question is. So I want you to go in the breakout room, and we're going to start talking about how FPGAs distribute clock. So the key question I want you to think about and discuss is, do we need special routing resources for clocks? Okay. So should we build something special in our FPGA for clocks? The alternative is, or we just use regular routing. Right, we have this highly flexible routing architecture. We can connect anything with it, including we can connect the clock signals of flip-flops using just regular routing. So maybe we're already done. You learned how to make a routing architecture. We don't need to do anything else. Or are there problems with using regular routing for clocks? Okay, so hopefully those questions are all clear. And I'm going to send everyone off into breakout rooms. And we'll come back in a few minutes.
Just like there aren't as many options as there are for logic routing, but there is some programmability in the clock networks.
Yeah, and like I didn't mean inside the logic blocks. Like I meant at the lower level, right before entering, like for example, a logic block. But
Oh,
yeah.
okay.
So I see. Professor stepped in. We were talking that about that we wouldn't be like it wouldn't be viable or a good thing to use regular routing because of clock skews. I think that's what Gil said.
Yeah, that makes sense. So it takes 60 minutes to work out
skews and also just racing your data. If your data and clock race each other, you are in trouble.
Right. Okay, so you're worried about skew basically. Can you make a low skew network? Yeah.
Can you?
Yeah. With an H tree.
Right. Okay. So you want to build an H tree, and are you worried that you can't do that with regular routing?
Would be very expensive.
I think one of the other points that Iggy mentioned was about flexibility, right? So maybe that's what one is going to. Right?
You don't need as much.
You don't need that much flexibility, so we could probably do it using the regular routing, but.
Yeah. So aside from skew, any other concerns about using regular routing?
Besides just taking up a lot of it.
Yeah, so it could be inefficient. So you're right. So that's a concern. Like maybe you can't build a low skew tree. Maybe you can, but you waste a lot of wire. Those are both certainly.
Well, another thing is it's going to eat a lot of power compared to a lot of other signals, considering a clock is going to, by definition, change as much as it can.
Right. Okay. So if you build even build a low skew network, if it's built in kind of a inefficient way using local routing or regular routing, that could burn extra power, and that's a big deal for a clock. Yeah, those are all good points. Anything else you worry about? So clocks can limit your speed, certainly with skew. That's one thing. Have you heard of clock jitter? You know what clock jitter is? You've thought about what causes it and what it leads to.
Yeah, I think so. Yeah.
So I'm putting you on the spot, but what do you think? What do you think? What is jitter, and how might regular?
Yeah. I guess you'd have to put an extra slack to make sure that even if the clock doesn't get you exact, to make sure that if you did it in a routing that's not as reliable. But that's assuming your clock network is more reliable than your regular routing there in terms of delay.
Yeah, that makes sense. Okay, sounds like you guys had a good discussion. I'm going to try to figure out how to leave so I can bring back the class. So sounds trivial, but I
see a leave room button on the bottom right if I move my mouse down so the menu comes up.
That makes sense. We've got like two computers and I always forget which one is controlling Zoom and which one is the slave, so I get baffled. Great, thanks a lot.
Thank you.
Yeah, hi everybody. I was muted. I was in two breakout rooms at once. So, did you have a good discussion? Did you come up with any ideas?
Yes.
Okay, I'm going to bring the class back, and hopefully we'll get a chance to hear about them. So. Can everybody back? Can everybody hear me? Looks like a few people are still coming back. Sorry, it took me a while to. Was joining multiple breakout rooms, and I have 2 computers running, so it took me a few minutes to figure out, a few minutes longer than I expected to figure out how to shut the breakout rooms down again. So hopefully, didn't run out of things to chat about. Okay, so does anybody want to share what they thought about or what you talked about? You know, what do you think? Do we need dedicated clock networks or not? Okay, yeah. Okay, looks like most people think dedicated networks are definitely needed. Let's see. Okay, why? Anybody want to share a reason? Okay. Okay, so the high fan out, we don't need much flexibility, so we can basically be more efficient by taking advantage of the fact that clocks are known to be high fan out and probably need less flexibility. So we can save some area, so it makes sense. Let's see. She says to manage delay, phase difference, fan outs. Camilo says they're not needed strictly, just true. You could build an FPGA without any dedicated clock networks, but your timing would be hurt because you've got high fan out. Dedicated blocks handles delay, skew, generation. Yeah, that's a good point by Michael. So we also need dedicated blocks to generate clocks. We could have those, PLLs and DLLs. We could have them drive regular routing, and they can drive regular routing, but they also can drive these dedicated networks. So we kind of got a logical place of we know what some of the sources will be for these dedicated networks, which makes it a bit easier to architect them. So yes, these are all good ideas, and I have some thoughts that I've put down here on why. So again, it parallels what I heard in the breakout rooms. So you guys came up with a lot of good ideas. So you can build clocks from regular routing, but clocks are different than data. Data, unless you have a hold time violation, which is usually you don't have a hold time violation, you want your data path to be fast. Okay, so you want a low delay routing algorithm, especially for your critical path. But clocks are different. We don't actually want a low delay routing algorithm. We want low skew. So let's see if I can actually bring up a nice diagram here. Okay, so normally if I had, let's say I have a block here, and maybe this block is generating my clock, and I want it to go to, I've got a whole bunch of other spots in my FPGA, so here's a piece of my island-style-FPGA. And let's say I want it to go to a register that's in this logic block, and also a register that goes in this logic block. So a conventional routing algorithm is going to just route this for minimum wiring and minimum delay. And it may balance, depending on how critical it thinks the signal is, how much it pays attention to delay versus wiring. So it might come out, for example, and take a wire here, connect to a switch, go down here, connect to another switch, go over here, and go into this block. Okay, and it would also go into this block. So from a wiring perspective, this is pretty good. And if this was a data path, it's pretty good for timing. But the delay to this first register might be 1 nanosecond, and the delay to the second one might be 2.5 nanoseconds. And that's a significant clock skew. Okay, so that clock skew is going to hurt me because this first register, let's say that the clock arrives at it at, let's say the first register is here. Let's call that A. And this register B is the one that had the shorter clock delay. Okay, so now my clock has a 2.5 nanosecond delay to the first register, only a 1 nanosecond delay to the second register. That actually is, there's some logic in here, right? That actually is going to come right out of my clock cycle. Okay, so I need, if my clock cycle is, say, 3 nanoseconds, I actually have already lost 1.5 nanoseconds of my clock cycle because of the fact that, let's see if I get a better color here, because of the fact that this guy's launching late. Okay, so that's a pain. So you say, well, okay, then maybe, so that was bad. If I reverse this, so now let's say I look at some other path where the first delay is small okay? And the second delay is big. Okay, now it doesn't hurt my clock period. In fact, it helps it. But I'm probably, if this delay is not very big, so let's say that this data path delay now is just a little data path delay, and this only has a 1 nanosecond delay in between these two blocks, now I've got a hold time violation, right? My clock arrives at this register, it launches its data. 1 nanosecond later, um, that data gets here, and that's actually before my clock arrived, which means I've got data run through. So that's a hold time violation. That's also bad. So skew hurts me either way, right? Whether it's skew where my launching register is launching late, that hurts my clock period, or if it's skew where my launching register is launching early, that exposes me to hold time violations. So I don't really like skew. And a regular routing algorithm with regular segmented routing, the kind we have in an island style FPGA, is going to produce high skew routes. So I've shown here, this was a net with just 2 sinks, but many people highlighted the fact that clocks tend to be high fan out. So if I go and make this 10,000 or 100,000 sinks, this starts getting really complicated. It's got branches all over the place to many, many registers, and the delays to those different registers are not very similar. So I'm going to get skew. Now I can try to make a low skew routing algorithm. So if I made a low skew routing algorithm, so I changed my CAD tools, and my CAD tools, let's just go down here and let's draw this case again. Okay, so I've got, let's see, so here's my clock source, and it's trying to go to, a few destinations. Let's just say there's a register here, and there's a register here. So one is far, one is near. A low skew routing algorithm, what would happen is the router should actually try to maybe go to some medium point here, and then take a routing switch to get onto another wire, go in there, and take a different routing switch, go up here, maybe take a routing switch and go in there. Okay, and that's closer. If you trace out the delays here, they look closer. So maybe this one is now 1.5 nanoseconds, so it got slower. And maybe this one was 1.3 nanoseconds. So they're definitely closer. It's lower skew. But with 100,000 fan outs, this is actually, you're not going to get the skew to 0, even with a very clever algorithm, because basically this routing network wasn't built with enough flexibility for you to precisely balance skew. Several people also highlighted, well, you could also waste some wire, and that's true. Now I'm trying to build, in order to build skew balanced networks out of this regular wiring, I'm going to lose some efficiency in terms of how much wire I use. I'm going to have to sometimes, I could have gone, let's see if I can highlight this. So I could have gone using a pretty short path from, the clock source to this first destination, and instead I chose to use a much longer path because I've got to try to balance skew with a different long path that I had to have out to here. Okay, so that's going to increase my wiring usage. I've got to, even when it's possible for me to take a short path somewhere, I'm going to actually have to take a longer path to try to balance skew if I've got a really high fan out network. So a bunch of things that kind of make it difficult for even a CAD flow that has a low skew routing algorithm to do a really good job. Okay, so we just talked about it's still not going to build a really low skew routing topology. And as clock frequencies keep going up, that's a problem, right? We don't want to lose a large fraction of our clock period to skew. Okay, so what about this? So do you know what I mean by crosstalk will add jitter? If anybody knows what I mean by jitter, what do I mean by crosstalk? This is one where if you want to, you can unmute yourself and just tell me, like, what do I mean by this? Why is this a problem? Yeah, so clocks aren't actually perfect. So if you have a 250 megahertz clock, if it was perfect, every clock edge is exactly 4 nanoseconds apart, but they're not really perfect. And crosstalk is one of the things that makes them imperfect. So do you know what I mean by crosstalk?
I thought I would just unmute myself for this, Professor. Yeah, it's basically when you have two signals that are causing some type of influence on each other that's undesired. So it's similar to coupling. So it can be from capacitive effects or inductive effects. But yeah, basically when you have two signals that are fairly close to each other and you start getting weird effects just from that.
Yep. Yeah, that's a great. That is a great answer. That's exactly right. So it's two signals that are influencing each other. They're coupled through their capacitance, either capacitively or inductively coupled. Both can cause crosstalk. On chips, it's capacitive crosstalk that's dominant. Inductive crosstalk actually can be important at the IOs and on the board, but on the chip, it's capacitive crosstalk. Okay, so what do I mean by that? So let's take my little route here, and I've basically gone in and I've created the best low skew pattern I could, given the regular routing algorithm, given the regular routing. But there are other wires around. Okay, so there's another routing wire here that maybe some other block. Let me change my color here. Okay, so there's another routing wire here. Let's draw it in blue. And this other block is using that routing wire. So maybe it's using that routing wire to go over here and keep going off to somebody else here. Okay. So if this blue routing wire switches at the same time as my clock wire here switches, there is a capacitance in between them. Okay, so these two wires are beside each other, so there's actually a capacitance between them. And that means if this blue wire rises, it actually makes the purple wire, the clock wire that I've circled here, also tends to rise because it's capacitively coupled. Okay? So that means if it was about to send out a rising edge, that edge is actually going to be extra fast. The delay of this wire that I've circled here is going to be reduced if the blue wire is transitioning in the same direction at the same time. If they're going in opposite directions, so let's say the blue wire right at the rising edge of the clock is actually discharging. Okay, that's actually going to slow down what happens on the clock. So now the clock's going to be delayed. So this difference between them is jitter. Okay, so some clock periods, the edge is a little bit early. Some clock periods, the edge is a little bit late. And there are a variety of reasons for that. But one of the big reasons is capacitive crosstalk, so coupling to nearby signals. FPGA timing analysis tools have to take that into account. So they basically have to assume that this clock, they have to assume the worst case. So they don't actually assume exactly one delay for when I launch my data and when I receive my data. They assume a range in both cases. And the width of that range is the amount of jitter. And the wider that range is, the more it hurts you, because jitter hurts you in both directions. Okay, it will hurt you in your clock period because you have to assume, for example, here I'd have to assume the clock arrives late. It will also hurt me on hold because for hold I'll have to assume the clock arrives early. So for jitter, it makes things ranges, and the timing analysis tool always takes the worst point in the range, which sometimes is the early one, sometimes is the late one. So jitter is really nasty. You want to keep it as low as you can. And your challenge is basically this: the regular routing network fundamentally just has wires that are beside each other. Okay, that's done because you got a lot of routing wires to lay out. So you space them out as much as you can, but that's still not that far apart. So there's significant capacitance between them. And that capacitance means that the switching on one affects the switching on the other. Okay, so that's going to add jitter. The next thing is another source of clock uncertainty. So jitter is a form of clock uncertainty, which, as I said, hurts your timing for both hold and setup, is variation. So you don't really know exactly how fast any one transistor is. You don't know the exact capacitance of any one wire. FPGA timing models actually assume, again, the worst value. You know, would a fast value or a slow value hurt me on this kind of analysis? And they'll assume the worst value that could happen on that chip. And regular routing is not optimized for variation. It's basically optimized to be dense. I need to get a lot of wires in a small area, and it's optimized for speed. given that constraint, if I got to fit you in a relatively small area, try to make the wires as fast as possible. That is different than saying I want to make the wires have as little variation in delay as possible. But for clocks, that's actually what you want. Okay, I guess I just talked about this. So skew is going to hurt me in timing, either setup or hold, depending on which direction it's in. And clock uncertainty, which is due to either crosstalk or variation. So the time models take into account both, is going to hurt both of them. And so in Cordis, when you actually look at the timing report, you'll see they actually report clock uncertainty. So the clock uncertainty is coming from this, right? Crosstalk and variation. Okay, and I see one last, actually, and the last comment by Camilo, which is a good one, is that clocks have a very high toggle rate, right? They change, they go up and down every single cycle, okay? So that is actually a 200% activity. They don't change once per clock cycle, they change twice per clock cycle. Regular data values, if you just have random logic, it's just doing all sorts of random stuff, then it can toggle every second cycle on average, 50% toggle rate, because it might be a 1, it might be a 0. Most logic's lower than that. Clock is 200%. So very fast toggling, which means we don't want extra capacitance or extra energy taken for a clock toggle because they toggle so much. So that is actually, another thing now that we worry about with what I showed you with this low skew routing algorithm, where it tends to use more wire than the minimum. I'm worried about the power of that too. So that's also a good point. So a bunch of reasons that clocks are worth building special networks for. Okay, so how do we do that? So convinced that we need special networks, what do we build? Okay, so a classic clock distribution style, which is used heavily by ASICs, is called an H-tree. And it's called an H-tree because it looks like a whole bunch of H's stuck together, right? So here's my first H, here's the second H, and so on. Okay, so the name H-tree is pretty literal. You basically drive an H-tree at the start. So here I'm making that programmable by putting a little routing mux in, so I can choose what signal goes through a pretty big clock buffer and onto the first wire in my H-tree. That goes significant distance, then it goes through another buffer on each side, goes to another wire, and so on. Okay, so I could pre-build this whole thing, which is like an ASIC-like structure. And the programmability would just be who drives me. Okay, so put a routing mux at the start. Now, why is this useful? Because the distance that I pass from this start point to any flip-flop, so here, let me draw this better. This flip-flop is pretty close to my drive point. This flip-flop flip-flop B is pretty far from my drive point, whereas flip-flop A is pretty close. But if I actually look at the wiring I go through, the number of buffers I go through to get to A is actually the same as the wiring I go through and the number of buffers I go through to get to B. So they are low skew, right? A is slowed down so that it has the same delay to get to A as to B. So low skew, because I'm building this special network, I can build it differently. And they are built differently. So what we do in clock networks for FPGAs is you actually lay out most capacitance between wires is actually wires in the same layer in an integrated circuit. So here's a certain wire, and on the same layer next to it, let me get a different color here. In regular routing, I'd have another wire next to me, okay? And I'm now worried about the fact that those are going to form a parallel plate capacitor, and I'm going to get crosstalk. So what do I do in this clock network? Well, I build that wire next to the clock, but I'm going to ground it. Okay, so I tie it to ground and it's not used. And I do the same thing on the other side, right? Build a wire and I tie it to ground. So it's actually just wired to ground on the chip permanently. And that means that it actually can help me be, well, it can be wired to ground or wired to VCC. It doesn't really matter. It just basically has to be connected to something that will not change. If it will not change, then it will not cause crosstalk. So maybe I'll tie this one instead of to ground. I'm going to tie it to VCC. So I actually have to distribute power and ground throughout my chip. So I'm going to do that anyway. And what I do is I basically lay this out with the clock branches, these various wires that I need for clocking in between. Okay, so this purple and this green wire, which represent things that I can use for clocks, are shielded. I've put wires that are either VCC or ground on both sides of them. And basically almost all my capacitance is to the wire right next to me. So from this clock's perspective, there's capacitance to that shielding wire. There's also capacitance to this shielding wire, but there is not any significant capacitance to this other wire, which can change because it's basically shielded by these closer wires that are connected to VCC or to ground. Okay, so I get rid of my crosstalk. Let's see. Did I just give each clock its own layer? No, I don't have to give each clock its own layer. So you're right that above this, if I was to look at the layer, hopefully you can understand what I'm drawing here. I guess if I draw this in a different direction, let me draw the edge view. Okay, so that's kind of the above view, okay, of one layer. So that's a single layer that I just drew. And now let me get all my colors here. So let's look at this purple wire. That's my clock. I'm now drawing it from the end view, okay? And I've got my shielding wires beside it. So here's one shielding wire. Here's the other shielding wire. And I think Diana's question is, well, what's above it? There are other wires above it. So on this layer above it, there's a wire or a whole bunch of wires. And on the layer below it, there are a whole bunch of wires. They're going in the other direction, okay? Because they're going in the other direction, there is a capacitance to this clock, but it's very small because they're not parallel for very long. These wires are perpendicular to each other. There are a lot of different wires crossing it, but that's actually good because if they're all doing different things, some of them are transitioning, some of them aren't transitioning at the same time, some are transitioning up, some are transitioning down, they tend to cancel out. So having, so the capacitance to these wires in the above and below is much less of an issue because first, the capacitance is smaller. This actually is further apart. And secondly, there's a whole bunch of little capacitances to different wires. And if you add up, okay, what's the net effect of those wires kind of transitioning at random? It doesn't add up to nearly as much. Does that make sense? And this means that, yeah, I'm not giving every clock its own layer because I still, on one layer, I can fit a bunch of different, clock wires. So I can put this green one and that might be part of another clock network. The last thing we do is we spend some area. So we use wider metal and bigger buffers to minimize variation. So if I was making routing wires, the wires might be like this, relatively low down in the metal stack, relatively small, relatively closely spaced out. Let me make them more closely spaced out because I need to get a lot of them in. And these clock wires are more like I've drawn up here. Let's see, let's highlight that. More like I've drawn up here. Higher in the metal stack, wide wires, widely spaced. And I make these buffers pretty big too. Why do I make them big? Partly the wires have to go a long distance, so I don't want them to be very resistive. So making them high in the metal stack out of wide metal is useful. And partly I don't want much variation. So if I make my buffers big and I make my wires big, the uncertainty in how strong they are is smaller. You get the highest variation in delay when you make things really small. And the difference of, literally 1 or 2 atoms in how big that transistor is or how thick the oxide is, makes a big difference. As you make things bigger, you get less variation. So that helps me as well with essentially my clock uncertainty. Does this all make sense? So I could do this. I could basically, for every clock I want in my FPGA, go build an H tree using the technique I just talked about, have programmability just at the source, and it'll work, and it'll be a pretty good clock. Okay, but there's a problem. We can have a lot of clocks in an FPGA design. So it's surprising, but you can have, it's pretty common. Well, it's common to have lots of clocks, and you can easily have real designs that have over 100 clocks in an FPGA design, which sounds like a shocking number because you're correctly told you should minimize your number of clocks to simplify your design. Why do we wind up with so many clocks? Well, you get a lot near the IOs. So FPGAs, we talked earlier in the course about programmable IOs, one of their big benefits. So all those different IO standards use different clocks. A single IO standard usually uses multiple clocks. So, for example, to go to double data rate RAMs, Altera's IP cores to go to DDR3, for example, need 5 to 7 clocks because they're gradually going from the relatively slow fabric speed up to the higher speed at the IOs, and they actually have to do some complicated creation of strobes and so on. So there's a bunch of extra complexity to essentially speed up the IO interface and then also make sure we can capture data reliably. So some of these clocks are big. Whoops. Let's see. What have I done there? Okay, thanks. Thank you, PowerPoint. But a lot of them are small. So we get a few major system clocks where we're doing most of our processing, and then a lot of little ones near the IOs. And maybe we have just one system clock, but a lot of the times we will be bringing data in from different IOs, and we'll have multiple system clocks that are pretty big, working near a certain group of IOs. Sometimes we're translating between IOs. Okay, so if we have 100 different clocks in some designs, should we pre-build, 100 clock trees? Let's see if I can get rid of this thing. And that's going to be really expensive, right? We could build 100 H trees using the technique that I just showed you here. But that would mean about 100 wires per channel when I get down to the bottom of the H tree. Okay, so it's the bottom of the H tree that I care about. When I get down to this point, I start having lots of wires at the end. If I built 100 H trees, I get 100 wires for every single channel at the bottom part of those H trees. The channel width for commercial FPGAs is typically about 200 to 300 wires in a routing channel, so adding another 100 wires is a big deal, especially because the 100 wires I'll be adding would tend to be these thick wires with big drivers and so on. So that's problematic. So what can we do? And I see Camilo's already got an idea. So if we know that a lot of these clocks are needed near the IOs, so could we do something special near the IOs? And that's a good idea. We know that we can have 100 clocks, but in order to have 100 clocks, a lot of them are going to be small, and we actually know where a lot of those small clocks are going to be. They're going to be near the IOs. So we can use that to say, let's build some special stuff near the IOs. Okay, so that's a good idea. Don't build 100 of these big clock trees. Let's build some smaller ones, and we also know where some of those smaller ones should be, out near the IOs. This is kind of a tricky one. Any other ideas? So that's a good idea. Anything else we can do? Which is it's probably a very difficult question. So seeing if you can, if you read the UltraScale Plus paper, it might have given you some ideas on this. So I'll give you a second to see if the class can infer any more ideas, and then I'll tell you some of the things people do. Can the clocks share routing channels? Yeah, so that is another really good idea. So sitting here is a good idea. The fact that we have 100 clocks in the whole chip doesn't mean we have 100 clocks everywhere in the chip. So maybe we can do some sharing, some multiplexing, and that's another key technique for making this more efficient. And actually, it's a good idea as well. So if some of the clocks are localized to parts of the routing fabric, so we can do that too. So let's go look at those. So one idea is essentially what you guys just suggested. Build some big and some small networks. So we can't have 100 clocks that go everywhere. Like that's not going to happen in a design. So we could build some big clocks, and a common one that's been used in a bunch of FPGAs, including some of the Intel ones that I'm most familiar with, is to build, for example, 16 global clock trees. So global meaning they're like full chip H trees. They look just like what I drew, right? So we've got some programmability of how do you get on this. And you don't build one of those H trees, you build, for example, 16 of them. They go everywhere. Okay, 16 is still not enough for 100 clocks though. So what are we going to do to get to 100 clocks? Well, we can build some smaller H trees. So what I've shown here is these red ones are also H trees, but their drive point is in the middle of a quadrant, and they only cover a quadrant. Now, the nice thing about if I build, I could build 16 of these H trees. So let's say, again, I do 16 here that cover a quadrant. And essentially, the cost of that in wiring and buffers is the same as building 16 H trees that cover the whole chip. Okay, so I can get not 16, but 64 of these quadrant clocks for the cost of 16 full chip H trees. So again, it's a common technique as well. So build some big H trees that cover the whole chip, build some smaller H trees that cover a smaller part of the chip. And you can build smaller ones still. And for example, you can have some smaller H trees near the IOs. Or if a clock gets small enough, you don't have to build a full H tree. At the point where you decide that the region that a clock spans is really small, you might be able to get by with just a fast wire that's driven in the middle. But it has to be pretty small for that. Okay, so that's the first thing. Build some big networks, some small networks. Everything that's not really small is still an H tree, but not necessarily as big an H tree. Okay, and then the second idea is essentially Senhyun's idea, which is, can we do some muxing? Do we really need to build all of this independently, or can we share it in some way? And we can. So a common technique here is the top part of a clock tree is not that expensive, right? So this is 16 clock trees, but let's just pick one of them. That's one wire, okay? It's a pretty long wire, spans half the chip, but it's just one wire per clock network. By the time I get down, if I kept drawing out this H tree, by the time I get to the end of the H tree, I'm going to have one wire in every single routing channel. So if I looked across the chip, I would find that there are a lot of wires to finish off the last little bit, the leaf nodes of each one of my H trees. So that's where things get really expensive. Not at the top of the H tree, not near the root, but near the leaves, because it's basically a branching structure. So what we could do is we're going to build 16 of these clocks that cover the whole chip, and then we're going to build 16 per quadrant. So that's what we showed on the previous slide. But we don't want to build at the bottom of this. We don't want to build 32 sets of leaves, basically, right? 32 sets of wires per channel to finish off these H trees. What we're going to do is instead we're going to do some muxing. We're going to say, once we get down near the leaves, we're not going to build all the bottom parts of these H trees. We're going to build, in Intel chips, they actually choose 6, okay, for most of their chips. So they'll build 6 wires that span a portion of a row. Most of their chips, it's 1/8 of a row. And that's the last part of the clock tree. Okay, now 6 is less than 32. There are 32 different clocks that could have made it down to this little part of the chip, and I only built 6 final pieces of the clock network. So what we do is we put in routing muxes, okay? Routing muxes that allow us to pick from these 32 signals, we can pick 6 distinct signals and put them onto this final stage of the clock network. So this last stage of the clock network also, because I'm spanning 1/8 of a row, that's not really an H tree. If I wanted to keep making the last piece of an H tree, I'd have to still keep branching this down until I was down to one logic block. Basically, once you get close to your destination, the skew from just using one wire at the end is not that bad. So when you get close enough, FPGAs usually switch to what's called the spine and rib clock. Spine and rib means I just got a wire, and I'm going to pull a whole bunch, which is called the spine, and I'm going to pull a whole bunch of ribs off of it. Okay, so it's a bit cheaper than an H tree, even though it's not quite as low skew. So you only want to use it when you're near your destination. And I don't want to really build all the ribs, these things, because I'm going to build one of those in every single row. Well, every piece of a row is going to get one of those. So I built, in Intel chips, for example, 6. Now this puts a constraint on me. I can never, in this 1/8 of a chip, or 1/8 of a row, I cannot use more than 6 clocks. So, but there are possibly, there might be 32 different clocks that wanted to get here. Okay, so what can I do? This is where you use your CAD tools, right? So the CAD tools, during placement, monitor how many distinct clocks am I trying to use in this piece of a row, and they will not accept any placement that tries to listen to more than 6 clocks in this clock region, this piece of a row. So the CAD tools forbid it. and that's okay. So if you made this too low, right? If I said instead of 6, I had only 1 clock could come here. This is an architecture experiment. You would see, well, what happens if I do that? And when I was at Altera, we did that, and the result is bad. Okay, that's too strong a constraint on the placement engine. It has to start doing weird things to try to meet that constraint. If you go all the way to 6, the placement engine is pretty happy. It's not very hard for it to perturb the placement to enforce that, because you usually don't get, clocks tend to separate out some, and 1/8 of a row is not that big a region. Does this make sense? So any questions on that? I guess when I can't see you, I have to reverse the sense of my questions. Okay, so I don't see any questions, so we take that as hopefully understanding. Okay, what I just showed you was the kind of the dominant clock network for quite a few years, but it's gotten a little more complicated in the most recent FPGAs. So Stratix 10 from Intel and Versal from Xilinx has also adopted a somewhat similar approach. Okay, so what are they doing in the absolute latest FPGAs? It's a kind of a hybrid approach. So they divide the chip into relatively big pieces that they call sectors. Okay, so this is what Stratix 10 calls it. Xilinx is a slightly different terminology. But basically they create these clock sectors that are a reasonably big chunk of the chip. And in Stratix 10, for example, there usually be about 64 sectors in a chip. Within the sector, the clocking looks like what I just showed you. Okay, so they basically build part of an H tree. At the very bottom, they go to spine and rib. They have the muxing that I showed you at the leaves. So that's basically what I just showed you is now what's inside one of these sectors. But above the sectors, they've made it more flexible. Basically, above the sectors in Stratix 10, they just have 32 routing wires. Okay, and those 32 routing wires per essentially clock routing channel, they're all shielded. They're all have big drivers. They're all on wide metal, so they have all the nice characteristics we want to get low jitter. But basically, they can be connected by switch blocks in relatively flexible ways. So the CAD tools now get to decide how are they going to use these 32 top-level routing channel, like these top-level routing wires for a clock network. They could build one big H tree that covers the whole chip, and looking like what I've shown on the left. So they can still build that. Basically, if they build the top part of the H tree out of this flexible wiring, then the bottom part of it will be constructed by the wiring within a sector. So they can still do that. But they can also build more irregular things. They can basically build, parts of it. They can build smaller H trees, and that's what they've done here. They built a small H tree. They built irregular H trees where this one doesn't go everywhere. It just turned out that it needed to go to the top of the chip and the bottom left, so they can build a tree that just covers those. And some of the other clocking resources are still available to be used by other clocks. So same idea, but they've made it a bit more flexible of how you construct the top level of the clocking. But again, using shielded large wires that are special so that we get low jitter. And basically, we can use this to build. We can build this exact structure again. 16 clocks per quadrant plus 16 global clocks. But we can build a bunch of other things as long as it never uses more than 32 of these clock wires in any particular region. Okay. And Michael's asking, can you replicate the fractal indefinitely? Yeah, so an H tree is essentially a fractal pattern. You're right. You just keep doing it. Basically, what happens with an H tree is you could replicate it till you're down to a single logic block, but people stop because once you get down to a small enough region, you normally just go to this kind of spine and rib pattern where you just take a wire and go a certain distance and finish off reaching all the clock destinations. It saves wiring versus doing the H tree fractal pattern basically down to the point where you've got individual logic blocks. So this last little bit can get small enough that they just kind of remove that and say, let's just cover that last bit with just a wire. And that's essentially what I'm showing here. That's this last rib. Okay. Okay, let's talk about Xilinx a bit. So, as I said, there's more similarities than differences. So mostly what I just told you about is very similar in Xilinx. They did some interesting things at UltraScale. They're 14 nanometer part, or UltraScale Plus, and they've carried it forward to their more recent parts as well. Okay, so what did they do? They had the same idea of there's these fat wires and big buffers that are distributing your clocks, and then they mux. That's essentially you're building a bunch of H trees. And then at some point, you have some multiplexers, and in their case, they have 24 different clocks they can distribute essentially throughout a region of the chip. And then they have 16 muxes that they can choose 16 of those clock sources, and they don't send them on one part of a row. They basically send them what they call a clock region, which is part of a column. But it's the same idea. They just rotated things by 90 degrees. So they pick whatever clocks you needed from the pool of clocks that are flying by, and this is their last rib, basically. This is what gets you to a fraction of a column, so maybe 1/8 of a column in the chip. And all the logic blocks on either side of that column can now they can pick one of those 16 clocks. They have some muxes to listen to that. But what they also did is they didn't just build muxes to select what clock they want to send on this final stage, this final rib. They also put in what they call a time borrowing circuit and a clock enable circuit. Okay, so they put a little bit of extra logic in there. Okay, so what is in this time borrowing circuit? The clock enable circuit just basically is, essentially a little bit more complicated than the AND gate, and allows them to stop this signal from toggling when nobody's paying attention to it, and that saves power. So that's why they have the clock enable circuit. The time borrowing circuit is a bit more interesting and unique. They build a delay chain. Okay, so the clock comes in here. It goes through a chain of inverters or buffers, which is basically just giving us different delayed versions of the clock. And they have a mux controlled by some SRAM cells that allows them to pick the clock after different amounts of delay and send it out. Okay, so they can send the clock straight through with no delay, or they can basically send it through a longer path with more delay. Okay, so they've put in programmable delay chains so they can delay the clocks. And it's pretty cheap. The reason it's cheap is they didn't put those delay chains inside each logic block right near the registers. They pushed them back to the level before that, this spine clock or rib clock. And that's going to mean that they're shared they don't need to build very many delay chains, right? So they build 16 of these time borrowing circuits, and that's going to be all they need for what they call a clock region, which again is maybe 1/8 of a column in the chip. So the cost of building those delay chains is very low because they're not building that many of them. And what it allows them to do is they can now delay or skew the clock to some registers. And this is a technique that now you've seen multiple times. It allows you to borrow time from one transfer, right? So I've got a very difficult timing constraint, lots of delay here. I can basically delay the clock to this one, and I can gain a bit of extra time, right? That's going to allow me to meet timing on that. And it's most useful on the highest speed clocks, where these relatively small delays could be a significant fraction of the clock period. This is a bit like retiming. So retiming would say if this timing constraint is really tough, right? So maybe this has a high delay and I'm failing a timing constraint, but I have some extra slack on this downstream timing constraint. You could try to move a lookup table back here. So that's retiming. But that's kind of granular. either this lookup table is going to be on this side or it's going to be on this side of the logic. And there are some constraints where sometimes I may not be able to move it. This delay can be much less granular, right? So it can be hundreds of picoseconds, so I can really fine tune how much time I want to basically give to this transfer at the expense of the right hand transfer. Okay, so yeah, the idea then is they can now pick. They've got a clock flying by, it's clock A. They can take that clock straight into a couple of CLBs to get the early version of the clock, and they can delay the clock through this delay chain and send that to another CLB. And now the timing transfer that I've highlighted in red here between these two logic blocks is easier. Okay, it's easier because the receiving logic block has a delay clock. In Versal, they go one step further. So they do another clever thing. Remember I mentioned that variation in the clock network leads to uncertainty in the clock. Like exactly when am I going to get a clock edge is a function of exactly how fast is every transistor on this clock network. So I have to model the worst case variation that might occur on any chip. Versal does something quite clever, where now that they have these delay chains on all of these last stage of their clocking, when you power the chip up, it actually measures the skew between the clock arriving at these logic blocks. So let me erase some of this. So it has some built-in circuitry where it would actually on power up measure when are the clocks arriving at these different logic blocks, and it would use that to decide, and they would compare their values with the logic blocks in the column over next to them, which are getting their clock through a different one of these clock spines. And if it turned out that these CLBs, let's call them alpha, were receiving their clock early compared to these other clocks, other logic blocks, call them beta, then the chip would actually use these delay chains, okay, to cancel out that difference. So you could actually, it would actually set some of these delay chains to slow down the clock to alpha. So in UltraScale, the CAD tools set these delay chains to allow you to basically borrow time from, take time from one transfer and use it for a different timing transfer. In Versal, they go one step but further. They still have the CAD tools use that, but the chip itself on power up will also measure for this specific chip what skew am I getting between columns of logic blocks, and basically adjust the delay chain settings so that it equalizes out that variation, and that allows them to reduce the guard bands in their timing models and run the chip faster. Okay. Whoops. Okay, so what did they get for this? So this is from UltraScale. It's not the Versal results. They show a few different things. So they put pulse latches in UltraScale, as we talked about before, in their logic blocks. And pulse latches, if you widen the pulse, you again can borrow time from the timing transfer on your input by stealing time from the timing transfer on your output if you're a flip-flop. So, and how much you can do that is a function of how much hold margin you have. If you have lots of hold margin, if it's okay for you to slow down, well, you have lots of data path delay on your output, then it's okay for you to do more of this because you have more hold margin. So they show what gains they get as a function of the hold margin. If you have lots of hold margin, so meaning hold time's not a big issue, we can use pretty wide pulses on our pulse latches, they can speed circuits up by about 5%, less if there's less hold margin. Or like if they have to assume, if they can, this is how much hold margin they have on the transfer. Sorry, I'm confusing myself. They compare that to what if they use this ability to skew the clocks, delay the clocks with this new technique they put in UltraScale, and they basically find skewing the clocks works even better. So that's what this green line is. Okay, so skewing the clocks, they can get a bigger gain, about 7%, and it's not as bad for hold time. So they can get most of those gains even if they don't have very much hold margin. And the two effects stack somewhat. If they have both pulse latches and they can skew the clocks, which is what they actually have in UltraScale Plus, they get a bigger gain. And these are, and they get the biggest gains also on the highest frequency clocks. So that's where you most need them. And that's not shown in this figure. This is kind of an average over a whole bunch of different designs. In this UltraScale Plus paper, they also say that their router was not trying to essentially get extra hold margin by slowing down certain data transfers that didn't have much hold margin. And if they could do that, they could probably get better results still. Okay, so that's all I had to say about clocks. Any questions on that? Okay, so no questions. Let's take a break for 5 minutes till 5:45, and then resume. Okay, on to the next topic, which is multi-chip integration. So FPGAs have been leaders in going beyond a single piece of silicon, and Xilinx really did some pioneering work there. It's pretty interesting. So the idea is to build a bigger chip, bigger FPGA, by combining multiple smaller dice. Okay, so this figure comes from Xilinx, and it shows you've got a typical FPGA laid out in columns of various things. And what Xilinx does for all three of the most recent generations is the big chips in a family aren't actually built out of one piece of silicon, like on the left. They're actually built out of multiple pieces of silicon, like on the right. Okay, so why would I do this? So you get better yield than a huge chip. So in a conventional chip, if you get a defect anywhere, so something goes wrong, it's not a very good color, let me change that color to something different. If I get a defect there, the whole chip is useless. Whereas if I get a defect on one of these three pieces, only that 1/3 is useless. I can basically still use the other two. Maybe I can find another third die and replace it. So I can get better yield, especially for big chips. And that lets you make really big chips. Okay, so at 28 nanometers, when Xilinx pioneered this technology, they made a chip with almost 2 million logic elements, and the largest standard FPGA that was built the traditional way, which is one piece of silicon, was about half that size. So, and there's a market for the biggest chip, right? So companies that are developing ASICs and just want to test or prototype on an FPGA generally just want the biggest FPGA that they can buy with almost no regard to cost. So there's always a market for these biggest chips. Also, the most complicated systems, so big communication systems that are going into core routers that drive the backbone of the internet, they tend to be pretty cost insensitive and also really like big chips. So being able to make big chips and yield them, that's the big advantage of this. Less big advantage, but still useful, is that we can save mass costs. So if I make a chip like this, if I repeat it 3 times, I get a 1.5 million logic element device. If I take 4 of them and stick them together, then I get a 4 million LE device or 2 million LE device, and I didn't have to make any more masks. And masks are expensive, right? So it depends on the process node and how mature that process node. But for state-of-the-art process nodes, the numbers are usually in the $5+ million range for a mask set. But we need to beat combining multiple chips on a board. If I could just package up each one of these things in a package and stick it on a board and it works fine, then there's no real purpose in me trying to make something new that combines them in some other way. But there are cases where these do win. So it is being used, and this particular strategy is used by Xilinx at 28 nanometers and all the families after that. Okay, so how do they do it? This is what, let me see, I can move around my picture here. This is what Vertex 7 looks like, which is the first chip where Xilinx did this. They have 28 nanometer FPGA dice. Okay, so they've got 4 of them in their biggest chips. That's what's up here, 28 nanometer chips. They take those chips and they flip them upside down. So this is where the transistors and all the wiring, etc., is on the bottom of this chip. Okay, so it's been flipped upside down, and the last thing you put on a chip like this is what's called micro bumps. So little solder bumps, but they're smaller than the solder bumps you would normally put on a chip to mount it into a package. So that's why they're called micro bumps. The micro bumps are, on the order of, I have to look at the exact technology, but on the order of say 50 microns, 30 microns. So much bigger than a wire, but significantly smaller than the regular bumps that you would use to connect to a package. Okay, so those micro bumps are connected not to a package, which is a package is basically like a fancy circuit board. They are connected to an interposer. So an interposer is another piece of silicon, and in this Vertex 7 part, it was 65 nanometers. So it's actually made using silicon technology on silicon, but it was a trailing edge process. So 65 nanometer is cheaper to make than 28 nanometer. And this interposer doesn't have any transistors on it. So it only has wires. But the wire is pretty dense, not as dense as 28 nanometers, but much more dense than what you could build using essentially traditional package substrate techniques. This green thing is the package substrate, which is basically a fancy circuit board. That's what's inside a package if you ever take it apart. Okay, so these micro bumps connect to the wiring of this interposer, and that interposer connects the micro bumps together, and that allows us to basically have connections that go between these different silicon dice. So they can get a lot of micro bumps on a chip. They can get about 10,000 or more micro bumps on one of these chips. So that's way more than the number of IOs you would get on a conventional chip. Conventional chip, you could get maybe 1,000, maybe a little more IOs. With micro bumps, they can get over 10,000. Okay, so that's giving us pretty dense interconnection between these pieces of silicon. But they've basically taken two chips, okay, the normal FPGA chip and this interposer chip here, and they've mounted them kind of the top of each facing each other, okay, so that their micro bumps melt together. They need to get some signals out of this sandwich to the circuit board, which is where this comes in. So they have to actually etch what are called through silicon vias. So vias right through the whole thickness of the silicon to get to some bigger bumps. These bumps are like the regular, what are called C4 bumps that you use to connect to a package. So they're same technology, but bigger. And those connect to the package here. Package, as I said, is like a fancy circuit board. So inside it is wiring. It connects to even bigger balls of solder called ball grid array solder balls, and those will connect to your real circuit board. So it's kind of a gradual move from very sophisticated manufacturing and very dense wiring to a little bit less sophisticated, a little bit less wiring on the silicon interposer, and then package substrate, and finally the circuit board. Okay. This is another picture of that. So FPGA die, and yeah, it's 40 microns between micro bumps in this picture. And TSMC makes this technology, and it's called chip on wafer on substrate. And the key different thing versus what you would get in normal semiconductor manufacturing is this interposer. Okay, so I said that a key reason for doing this, probably the biggest reason to do this, is to get better yield. So let's compare what yield we get if we just build a really big chip versus if we use this technique. Okay, so a simple but pretty reasonable yield model is called the Poisson yield model. And it basically just says the odds of a chip working is essentially exponential in its area. Well, it drops as its area goes up, and it drops as the defect density goes up. Essentially, this is the probability that you don't get a defect anywhere on your chip. So, the more defects you get per square centimeter, the lower that probability is, and the bigger your chip is, the lower that probability is. So if we take a big FPGA, say 600 square millimeters, which is around what the biggest FPGAs are, you can manufacture a chip that's about 800 or a little more than 800 square millimeters, but you can't really manufacture something bigger than that. So this is pretty big. And let's say it's early in the process. So processes get better over time. So when you first develop a new process, you've spent your whatever $20 billion to develop it. Your defect density is pretty high, and then as you run through many millions of chips, you learn what are various failure mechanisms, and you tweak it, and it gradually gets better. So early in the process lifetime, this would be a reasonable defect density, 1 defect per centimeter squared. So the odds of having 6 square centimeters of silicon that have no defects when I get a defect, on average once every square centimeter, are pretty low, right? So it's basically which chip. This is the only one where there are no dots. Okay, so that chip worked. Everything else on this piece of wafer is broken. So with these numbers, my yield would be 0.25%, so 1 in 400 chips. Wafers are 12 inches in diameter. So at this size of chip, I can fix 730 of them on the wafer. 730 square centimeters divided by 6, which is the size of my chip. So that's how many chips I have per wafer. That's the probability of it's working. I expect to get 0.3 working chips per wafer. So this is going to be an unbelievably expensive chip. It's also going to be a huge problem to actually meet it, basically supply this to customers, right? They're just going to be difficult to get enough chips to sell at any price. And the ones that you do get, you're going to have to sell for a very high price. FPGAs, end users want to get the latest and greatest FPGAs early. They do their design, and they expect that the price will gradually come down. So one of the issues you're going to have beyond just the price being high is that you probably can't just get enough working chips to satisfy the people who are trying to design with your FPGA when the process first comes up. And that's a problem, because if they can't design with your FPGA, they're actually not going to use it in their systems. So even as the process matures and this defect density comes down, if you didn't manage to get designed into systems, you won't be able to sell this chip as much. So just the number you can make is also an issue, as well as the cost. Okay, so let's say I didn't do this. I still want to make a really big FPGA, like that 2 million logic element Xilinx chip, but I'm going to make it out of 4 smaller chips, 4 1.5 centimeter squared chips. So this grid gets a lot smaller. And if I run through that same equation at the same defect density, the yield's much better. So now 13.5% of my chips work. And you can see why, right? So I've got the same density of dots, but there's just a lot of little chips where there are no defects anymore. Okay, so my die per wafer, I'm now going to get 66 working chips per wafer. Now I need 4 of those to make one system with the same capacity. But even if I divide those 66 by 4, I still get 16.5 systems per wafer, which is a 55 times increase in yield. So that's pretty good. And that's the key reason, again, that Xilinx did this. Intel has not embraced this technology as aggressively, which is interesting. And probably one of the reasons is, remember I mentioned, I think last lecture, that Intel's FPGAs are repairable. They build a small number of extra rows. So if they sell you a chip that has 100 rows of logic, it really has somewhere between, say, 104 rows, which means they can, as long as there's no more than one broken row in a region of 25 rows, they can repair it. They'll skip the broken row, and they'll basically program some fuses to tell the programming hardware that they have to skip that row. So Intel would not get the same yield improvement because they've already captured some of this yield improvement by making their chips repairable. So that's a different technique, which is also interesting. Okay, but this says if I don't have a repairable chip, early in the lifetime of a process for a big chip, it is a really big win. Let's look at a smaller chip. So the sort of workhorse, like kind of mid-range chip in an FPGA family is usually more like 2 centimeters squared. So it doesn't have as much logic capacity. It's got maybe 1/3 the logic capacity, but it's a lot cheaper to make. And the defect density does improve pretty rapidly on these processes. So for a mature process that's really been tuned, a reasonable defect density would be like 0.1 per centimeter squared. So if I run through the numbers with that, I get that 82% of my dice are going to work. And for a 12-inch wafer, I expect to get 299 working dice. If I make a system if I instead say I don't want to make a 2 centimeter square chip. I want to make a system out of 4 really little ones. My yield gets even better. So my yield's 95%. I will get more die per wafer. If I divide them by 4, because I have to take 4 to make a system of the same capacity, I do get more, right? I get 347 working systems versus 299. But at this point, it's unclear that that would actually cover the extra cost of I have to make an interposer, I have to have a more complicated process to basically combine these dice together with the interposer, and that's not going to have infinite yield. It has pretty good yield, but it's not going to be 100%. So this one is not clear. Probably for this smaller chip with a mature process, it's actually not worth the effort. But it is a pretty big win for the first case I gave, which is why Xilinx uses this for their biggest chips, and they don't use it for the smaller chips, because that's where it makes sense. Okay, so it sounds pretty good. Let's look at Vertex 7 and how much wiring they can basically get across these interposers. So this is a chip that actually has, it's made out of, maybe I'll draw this differently. It's basically made out of 4 pieces of silicon. So that's the first one, that's the second one, and so on. They have 280 columns, okay, like routing channels. So across this chip, there are 280 routing channels vertically. And normally those routing channels have 210 wires in them. So W equals 210. Now, they actually can't get all of those wires across the interposer. So the interposer provides, micro bumps, which is a lot better than what you can do in a normal package, but it's still not as good as, it's not as dense as the wiring you have on a single 28 nanometer chip. So where they cross between interposers, they can't get 210 wires across, they can only get 48 across. And to get 48 across, they basically have micro bumps all over this region near the interposer boundary. And that allows them to get 48 wires for each channel across the interposer. So if you do the math, that's about 23% of their vertical routing. So these are choke points. Wherever they cross the interposer, they get a lot more wiring than they would get if they were just 4 chips combined on a package, but quite a bit less than they would have had if they were one big chip. There's also an extra delay. So on this chip, the delay to go across the interposer is about a nanosecond, whereas the delay of their kind of workhorse length 6 vertical wire is about 200 picoseconds. So their vertical wire delay to cross an interposer is around 5 times what it would be if they were still within the same chip. Their Xilinx CAD flow, I think did a smart thing of basically it hides the fact from the user that this is really not one piece of silicon. So you just write your HDL, you synthesize it, you place and route it, and the fact that it's not one piece of silicon is basically invisible. You do not have to partition. So if you were making a system and you used 4 separate chips on the circuit board, you would have to decide what logic goes in each one of those chips, and you'd have to decide carefully or you'll run out of IOs. You don't have to do that when you use this chip. The CAD tools will figure it out for you. One of the things people do when they have to go, let's say ASIC prototyping people, when they use multiple FPGAs, is they run out of IOs all the time. If they're taking a big design and trying to put half at one chip and the other half in another chip, is you typically run out of IOs. So what you can do is you can slow your clock down and you can time domain multiplex these wires in between the chips. So you'll send multiple values in over several, you basically make your clock slow enough that you can run the IOs at maybe 10 times the rate of your internal clocks, and then you can send 10 values over each set of wires every clock cycle. So ASIC emulation tools often do this when they have to divide a chip up, an ASIC design up across multiple FPGAs for prototyping. Xilinx doesn't do that. They have enough signals crossing between the different dice that they don't have to time domain multiplex signals going across the boundary. So it looks like a single chip, which is good, right? So they can sell this then as one FPGA. And clearly Xilinx has modified their CAD tools to make this work well. So they've changed their placement engine to try to understand that crossing certain boundaries is slower and that they're interconnect choke points. So an interesting question is, well, how well is that going to work? And it's hard to get Xilinx just says it works great because they're selling the chip. There is an academic study that basically took VPR, so the tool you're going to use for assignment 4, modified it to make it understand there are these interposer cut lines where most of the routing doesn't cross. So most of the wiring just ends, some fraction crosses. So that's what happens in an interposer. And basically did architecture experiments to see how bad is it to have some of this wiring not cross the interposer. Does it matter? Does it not matter? So if you read that paper, it modifies the CAD algorithms. I'm not going to go through the details, but it is important to make the CAD tools understand this. And it's basically important in 2 places. When you're building logic blocks, it's important that you build them out of related logic that essentially could go in just one part of the chip. So using a partitioner to chop the design up into say 4 pieces and then only cluster within 1 quarter is helpful. So there are other techniques you could use, but basically it's important that if you're going to cluster into logic blocks, you understand that you make really sure that the logic you're putting together kind of belongs together, because otherwise you create more signal demand across those interposers. And then it's also important that you change the placement engine to understand that crossing certain lines that correspond to leaving the chip are a problem. You should really try to avoid doing that. Okay. So I'm not going to go through the details of it. In this paper, basically, those 2 changes reduce the amount of wires that cross the interposers by 35%. So pretty big gain. And the Xilinx tools are almost certainly better tuned than that still, because they've had longer to work on them and a bigger staff. But from this academic study, what did it find? It found that it's okay to cut about 80% of the wires. So this is basically showing how does the minimum channel width to route a suite of benchmark circuits change as we cut wires at interposer boundaries. So if we take an FPGA that's composed out of 4 pieces of silicon connected by an interposer, if we cut 80% of the wires at the interposer boundaries, our minimum channel width increases a little, but not much. If we cut, about 70%, the minimum channel width has hardly moved at all. So basically, as long as the interposer provides around 20%, maybe a little more than 20% of the wires that a regular routing channel provides, the CAD tools seem to be able to handle that pretty well. If they provide significantly less than that, the channel width starts getting bad. What this is indicating is that basically the tools are now being limited by how many signals can cross the interposer. It's starting to become the only thing that matters. So Xilinx basically cut 77% of the wires. So they're somewhere around here, which is basically in the spot that looks pretty good. And as I said, they probably also tuned their CAD tools pretty heavily, which may have helped them further. So that looks all pretty good. One challenge is that these micro bumps are not scaling at the same rate as the wires that are on the chips, which means that the fraction of wires that are cut is going to increase as we move, from 28 nanometer chips down to 16 and down to 7 nanometers and so on. We're going to wind up with a higher fraction of wires cut. So that's going to be a challenge. So maybe need some architecture improvements, puts pressure on the CAD tools too. So in the same paper, there's some architecture changes that can help this are for the wires that go across the interposer, make them easier to use. So put bigger routing muxes in front of them. And this is another case where bidirectional wires. So got a wire that's going to cross the interposer, right? So starts on a micro bump, goes across, goes to another chip. That is a precious resource because it's using a whole micro bump on each side. So instead of using a direct drive switch where it can only go one way, this is a case where you want to make extra big routing muxes on this, on this chip. Let's make this chip bigger. And you want to make the driver tri-statable so that you can send a signal this way. And on the other side, you also make it tri-statable so that you can send a signal the other way. So it's a case where tri-state buffers are still very useful because the wire is so expensive. So we don't want to use a direct drive switch where we can't tri-state the driver on this wire because the wire is rare and expensive. Okay, so that was Xilinx. I said Intel hasn't adopted this, well, in the same way, but in Stratix 10, they did start adopting interposers too, but a bit differently. So this is a kind of a schematic of Stratix 10. So the FPGA is one big piece of silicon, okay, whereas Xilinx is cutting their FPGAs, if they're large FPGAs, into multiple pieces of silicon. But the fast IOs, so these are the transceivers to do things like PCI Express and other high-speed protocols. Those are pretty big. When you get into serial IOs, we looked at them a few lectures ago. They're pretty complicated. They're actually pretty large. They put those on separate pieces of silicon. So they have multiple what they call chiplets, and the chiplets are basically for high-speed IO. And one advantage of that is they can actually use a different process technology for these IOs, and sometimes IOs like different flavors of process technology than your core fabric would like. And they can basically take several of these chiplets and combine them together with basically little interposers. So each of these green things is a little interposer that allows them to connect the big FPGA fabric to these IO chiplets. Okay, so this is a kind of cut through picture of what these two technologies look like. So Intel calls the interposer technology EMIB, and Xilinx uses TSMC's chip on wafer on substrate technology. Okay, so what Intel does is they have a single FPGA die. It uses regular big solder bumps to connect to the package. Okay, so they don't need through silicon vias. And then they also build these chiplets for I/O, and they use regular big solder bumps again to connect to the package, so they don't need through silicon vias either. And then they have little interposers. Okay, so this interposer doesn't go into the whole system; it just goes into part of it, and it basically bridges this I/O die to the FPGA. And they can have several, and do have several of these I/O die. So it's kind of more heterogeneous in a sense. They make several of these little I/O chiplets and then one big FPGA. Okay, and then Xilinx, as you saw before, makes several FPGA die that are all big, and they connect them with interposers. And they need through silicon vias now to get some signals out of that kind of sandwich. So there are trade-offs for both of these things. Because this interposer is limited by what's called the reticle limit, because it's made with silicon technology and it's one piece of silicon. It's limited by basically the maximum image size that the optical lithography can project. Okay, so the optical lithography systems all have a limit of about 800 square millimeters. So Xilinx can make really big FPGA systems, but currently not bigger than 800 square millimeters. They can yield them well because they're made out of multiple FPGA dice, but they can't kind of build an arbitrarily big FPGA because this interposer is going to limit them. And TSMC is working on some techniques to get past that, so that may change in the future. Intel, in theory, could make, if they actually use these embedded interconnect bridges to get multiple FPGA dice, which they have done in one product. In theory, they could kind of just keep making a bigger and bigger system. The other difference is Xilinx's technology uses these through silicon vias, and Intel's doesn't. Intel argues that might impact signal integrity on really high-speed IOs, because on really high-speed IOs, you have to pay careful attention to inductance. You want to minimize the inductance of the whole signal path. I have no real idea of how big an impact that is. Xilinx is able to make fast transceivers, so it doesn't seem like it's an enormous impact. And then something that's coming in the future is, so far these interposers, whether they're put together in the TSMC way or the Intel way, have been just wiring, right? They don't have any active devices. And future interposers are going to include, and they've been deployed in some processors already, do include transistors too. So when you move on to these more complicated fabrication technologies, an interesting question is, what should you build? Okay, so any questions on that topic, on interposers? I believe the Xilinx device was actually the first major use of TSMC's interposer technology. So it's another example of FPGAs tend to be aggressive adopters of state-of-the-art silicon technology because they're big chips and they can be sold for high prices. So they tend to really like the state-of-the-art technology. Okay, so the last thing I was going to cover today then is registered routing, which is something that academics had looked at a few times, but hadn't been deployed in any commercial FPGA until Stratix 10. So what's the motivation? So this is a pretty big change in FPGA architecture as well. So before this, all commercial FPGAs had registers in the logic and the RAM and the DSP blocks, but they didn't have them in the interconnect. Interconnect was wiring and muxes, or other programmable switches. So Stratix 10 was a big change to say, no, we're going to put registers right in the routing. So why did they do it? And there are a few reasons. So designs are becoming more register rich, and you can't cross the chip in one cycle. So that means you have a lot of paths that are, just register and then a wire or another wire, several wires in series and another register with no logic that's actually being done in between those two registers. So for paths like this, where you start on a register and end on a register, and all you have in between are wires, it's kind of annoying if I want to cross the chip, and I basically have a register, and I need to come out of that register, go to some wiring. Okay, so I've got a mux or some routing driver to get out there. I go through some routing switches, so I go through a few wires, and I go back. I can only make it partway across the chip, so I actually have to go back through a connection block mux, go into some local routing, go through a LUT, go into a register. So I got my register, and now I come back out through some other kind of switch block output mux and onto a wire, and I keep going. So to get into this block and to the register took some delay. It took about 300 picoseconds. And that delay was kind of wasted. I actually just want to get across the chip, but I can't do it in one clock cycle. So I have to go into a block to get a register, and I have to do that every once in a while. And every time I do it, I actually just add 300 picoseconds to my wiring delay. So that's going to mean that I have to register even more because every time I want to get a register, I lose 300 picoseconds of delay to get to the register. So if I want to cross the chip, I need to use even more registers because of this insertion delay. So the idea is, could we add registers to the routing wires themselves, which should be very useful for these kinds of paths. If we're going to do that, we want it to be low cost because most of our area in an FPGA is the routing. So it's obviously a pretty big risk to doing this. And we want the registers to be fast. Okay, so can we remove this? We're trying to get rid of this insertion delay. The fact that if we're crossing the chip, we really would just like to use wiring, but we can't. To go into a block to get to a register takes us around 300 picoseconds to get into that block and back out again. So it's kind of wasted delay. Could we get a lower insertion delay to put a register in if we don't have to go into a block? Okay, so that's what we're trying to achieve. What are the costs? Well, it's probably going to be harder to use the registers in the routing. The blocks in an FPGA have all sorts of muxes and local interconnect. So that's kind of what caused that insertion delay that we don't like. But on the other hand, it means that a lot of different routing wires can get into a certain logic block, which means those registers are more reachable, they're more usable. Okay, so whatever registers we put in the routing, they're going to be harder to get at from any particular, so we're probably going to waste a lot of them. We're going to make our CAD flow and our architecture more complicated. We're going to add area to our routing. Like there's no way we can add registers in the routing without costing some area. And we're also potentially going to slow down our routing switches, right? So if we're going to add registers into our routing switches, even if we can bypass them. So maybe we add the registers into the routing switch where we say, okay, we've got a routing wire, and now we can go into the register, come out again, or we could just bypass it, and there's a 2-to-1 mux. Okay, so same kind of thing we do with lookup tables. This is my big routing wire. And then I'm into my routing driver. So I've got a big buffer here and so on. Well, I did add this register. I did add this mux. They're going to cost me some area, and this mux is going to cost some delay even when I don't use it. So we expect we're going to take some hit on the speed of our routing wires. And then another question is, okay, I just drew a register here, and the register is, right at the end of this routing wire. What do I hook up to its clock? Okay, so we just talked about, we have these clock networks, we have all this muxing. All that is designed to get clocks into the registers and logic blocks and DSP blocks and so on. I need to think of how I'm going to get the right clock to this register, because if this routing wire is carrying a signal that came from some clock domain, clock 300 is maybe its name, then I need to make sure I get the clock 300 signal to this register. But that requires its own network of muxes, so that could get expensive as well. Okay, so what did StarX 10 do? So they didn't build an actual register. So they used this trick again of pulse latches are cheaper than registers, and if you make the pulse short enough, they behave like a register. So they need to make a whole lot of registers. They're going to make one for every single routing driver. So they want them cheap, so they built pulse latches. So what they added is the logic in dashed lines. Okay, so they've got, what do they usually have? They have a routing mux. Okay, so the routing mux, this is a direct drive switch. So I've got a routing mux. I've got my weak pull-up because this is built out of pass transistors. I've got a little inverter. I've got a big inverter, so that's my routing driver. So that's what I already had. Okay, so everything in red already existed. And the routing mux is the biggest thing. Okay, so these aren't all equal size. What did they add? They basically added the ability to turn this into a latch. And to do that, they basically built a latch out here, and they built a few control transistors that I don't think I want to go through right now, and they had to duplicate one of the inverters. So I don't think I want to go through the details of this. You can study the diagram and see how does this all work after the fact. But basically, they only added 10 transistors to the routing driver. So it's pretty small. And they compare that in the paper to how many transistors were in the original routing mux plus routing driver, all the things that I showed in red. And then they had 73 transistors in their original routing mux and routing driver and configuration RAMs to control it. So they've only added 10, and most of them are small. So they say 8 of them are minimum size, so the area is not too big. So they say that increases the area of their tile. So the logic plus routing tile, which they call a lab, increases by 5%. So that's not zero, but it's not enormous. However, they don't ever give a number for how much does the area increase when they include the fact that they have to get control. So there's this control logic here. This control logic is basically taking a clock pulse and looking at a configuration cell, like an SRAM cell, and then producing these control signals, latch enable and nlatch enable. So this is basically what controls these. It basically says, should I be a latch or not? Okay, so they do need some control logic that takes a clock pulse and a configuration that's been programmed in by the CAD tools, and either it permanently turns on, if it basically is not being used as a register, then it basically permanently turns on this transistor and this transistor, and this behaves like a regular routing driver. If you put I think it's a 1 in this cell, then it behaves like a latch. And you have to give it a clock pulse so that latch, given a small clock pulse, actually behaves like a register. Okay, so they don't, in the paper, say how much area this adds, but that's another, looks like 12 transistors. So there's some extra area there that's not negligible. And then they also have to create this clock pulse. So that's going to take some logic to select what clock should I have, and then to actually generate the pulse. So that's not accounted for either. So they never actually say in the paper, what does it all really cost? They just say this part of it is pretty cheap. From talking to people at Intel, I mean, the overall cost is not overwhelming. So it's more than 5%, but clearly small enough they thought it was worthwhile. And I can't bound it any closer than that. Any questions on that? So does this make sense to everyone? But it is a clever trick to get this many registers. It's a clever circuit trick of how can we basically make our route, reuse as much as we can for our routing drivers to make them also capable of being a latch. And then if we provide that latch with a short pulse, they behave like a register. Okay, so one of the challenges is how do I get that clock to that pulse latch, which I want to behave like a register? So when we're talking about clocking, you saw that in every row in an Intel FPGA, there's something called row clocks. So these row clocks are typically about 1/8 of the chip long. Or in Stratix 10, they're like a sector long. And that's what's passing by every tile. So every logic block, every RAM block, etc., as possible clocks you might want to use. So not all the clocks in the chip, but just the 6 that have made it down through the H trees and have been selected as these row clocks that are now accessible to the logic or RAM blocks, etc., in that region. So a logic block already picks typically it has muxes to pick 2 of these clocks and bring them in, and then the registers in the logic block can use those 2 clocks. But now with these registers, the clock or pulse latches they've added to the interconnect, they actually have a whole bunch of routing drivers in the same area as a logic block. So this is their basic tile. So the basic tile is a logic block, which they call it a lab. They have a whole bunch of what they call lab input muxes. Those are the input connection block muxes. And they have a whole bunch of what they call driver input muxes. Driver input muxes are the direct drive switches. So a mux and then a driver that can't be tri-stated. And they, in these pieces, this is basically W of these wires horizontally and W vertically. And they have one of these driver input mux for every single wire that starts right beside this logic block. So they wind up with 52 of these logic block input muxes because they have 52 inputs to the logic block. And they wind up with 4 groups of, they wind up with 200 of these routing drivers that are associated with a certain logic block. Okay, so that's a lot of routing muxes, right? That is 252 different muxes or routing drivers, each of which could now be a register. So they can't afford to build 252 separate muxing networks to choose, which of these clocks that is coming by am I going to use. So they couldn't build 252 6-to-1 muxes. It's just too expensive. So what they do instead is they basically they say that 50 of these driver input muxes can only pick from 2 clocks. So they build just 2 6-to-1 muxes, and that gives them 2 clocks. And now every one of those routing switches can choose between those 2. So every routing switch is going to get an extra 2-to-1 mux and an extra configuration cell. So that is going to cost some, but it's going to cost less than if they let them all pick from all 6 of the clocks. And they find for the limbs, the connection block input muxes, they can do even less. They can just have 1 mux that picks one of the 6 clocks that are running by, and then all of those 52 input connection block muxes, if they want to register a signal, they're going to have to use that clock. That's their only choice. Okay. yeah, so they basically come up with this scheme to figure out how can we make this multiplexing to select clocks cheaper. And they basically force a high degree of sharing. Uh, we're not going to let every one of these running switches just pick any clock that is flying by, which is one of these 6. They're going to have to be much more limited in their choices so we can keep the muxing cost low. So let me do a comprehension test here to see if anybody can think of this. So this means they also did less clocking flexibility for these libs, right? The connection block input muxes, because all 52 of them have to share the same clock. And they're not quite as restrictive for these driver input muxes here, which are just the muxes that connect running wires to each other. Those they divide into 4 different groups, and then each group still gets to pick between 2 different clocks. Each one of them gets to pick between 2 different clocks. So they've got a bit more flexibility. Why? Why do you think these limbs don't need as much flexibility in terms of which clock they use? This is probably a hard question, so if you have any idea. Yeah, so it's a great point by Evan. That's exactly why. So the logic within basically, the limbs are registering a signal as it goes into the logic block. And what's in a logic block tends to be related logic. That's what your whole clustering stage in a CAD tool is trying to do. Find things that are related, put them together so that we don't need so many inputs and outputs and so on. So what's inside this logic block is much more likely to have just one clock. And the logic block actually has a limit on how many clocks it can have anyway. So in most Intel chips, for sure, there are no more than 2 different clocks used in this logic block. So all the signals that want to get into the logic block should belong to commonly 1 clock domain, and probably in the worst case, 2 clock domains, because the logic block can't handle more than 2 in most Intel architectures. The DIMMs are different, right? The DIMMs, some of them could be, driving a signal that just came out of this logic block. Okay, so that's going to be on the same clock domain as this logic block. But some of them, let's see if I get a different color here. Some of them are going to be driving signals that are just flying by, right? So this signal might have come from halfway across the chip and it's just flying by here. There's no reason to believe it's on the same clock domain. So these switch block muxes or DIMMs have more diversity in what they want for clocks. And that's why they spend a little more area on giving them a bit more flexibility in the clock selection network. Okay, so how well does this work? You kind of saw this in that Xilinx UltraScale paper as well. What speed you get is going to depend on how bad your hold time is. So if you need to have, basically, if the hold time of the pulse latches is not very good, then you're going to be limited in, can I basically have a routing wire and driver? Let's get rid of that. Okay, so I've got a certain routing wire here, and then I'm just going to go to another routing wire, and so on. So I've got this repeated pattern of routing wires feeding each other. And I can turn this into a register, and I can also turn this into a register, well, into a pulse latch. But I may have problems basically having a pulse latch and then just one wire, okay, and then another pulse latch. And the reason is pulse latches don't have very good hold time. So they need a certain amount of signal delay in between them, or they can actually let the signal run through in one clock cycle, and that breaks your design. So depending on exactly how good or how bad the hold time is on these pulse latch registers, they're going to be able to use them more aggressively or less aggressively. And so that's why they give this curve. If the hold is pretty easy, right? So they don't have too much of a constraint on hold time. They get a certain F max. If the hold that they achieved, if they need to get 500 picoseconds of hold margin, meaning they needed to have at least 500 picoseconds of delay on this wire, which they're not going to get. So that would mean that they're not allowed to use 2 of these registers on consecutive wires. They'd have to have several. They have to use several wires in kind of the regular mode before they put another pulse latch in. Then they can't get as high a frequency because they can't use their pulse latches as much. They can't pipeline as deeply. So that's one of the key things, is that this technique is going to be impacted by exactly how good or how bad the hold time is on these pulse latches. Let's see. I see Camille's got a comment. The only time related logic of two clocks very close would be clock domain crossing FIFOs. Would they have a few blocks with two clocks for those cases? Would timing crossing too many logic clusters be good enough for this application? Okay, so I think your question is like, do I really need to build the ability to have two clocks inside one logic block or not? Or is it just so rare that you need to put two different sets of registers with different clocks in a logic block that you could say I just need to have one set of clocks in a logic block? Is that your question, Camille? Yeah, it's not catastrophic to just have one clock per logic block. So some FPGA architectures do say you only have one clock per logic block. Some will allow you to have two. I don't know of any that actually usually they don't allow more than two. And you're right. The cases where you have two clocks in a logic block tend to be things like clock domain crossing FIFOs and so on. So there are some cases. If your logic block says I can only have one clock per logic block, then you would just separate out those registers. So if I'm crossing between clock domains, well, you put some of the registers in one logic block and then put the registers clocked by the other domain in the logic block right next to it. And that's pretty good too. So it normally comes down to just you do CAD experiments and you see which one gets you better area. And one clock or two clocks both turn out to be reasonable answers, and somewhat dependent on how big your logic block is and how you choose to create your clock enables and some other things. Does that make sense? So it's not a hard limit of you must have two clocks per logic block. Most Intel chips have done that, but some, I believe, have actually gone down to one. And certainly we experimented with one, and it also works pretty well. Hopefully that answers your question. Okay, so this is hold time's a key barrier. So to summarize the Stratix 10 paper, they basically have a 5% area increase to add these pulse latches, which again is pretty good. They add them in every single routing driver, but it's not the whole story because they have some unspecified cost for selecting the clocks and for control, like basically choosing am I going to be a pulse latch or a regular routing driver. So we know the area cost is actually somewhat more than 5%. There is a small routing slowdown. So if we go back to this circuit, they haven't added anything on the path where you just go straight through and you're not using a latch. You still go through two inverters, okay? And you go through one mux. And so that means that this is still pretty fast as a regular routing driver, but it's not going to be quite as fast. The reason is putting these extra transistors in the pull up and pull down path are going to weaken this inverter. That's going to slow things down a little bit. Now this inverter is not really heavily loaded, so it shouldn't be too bad. The other thing that happens is the action of just adding more circuitry spreads everything out. So they've taken a more than 5% area hit. That does mean that their wires are going to get a bit longer, right? So the square root of 5% longer, basically. And that's going to cause them a little bit of slowdown too. So it's not going to be catastrophic, but their routing will slow down a little bit when they just use it as regular routing. They gain many more registers, and they can get at them without the logic block insertion delay. So they can retime logic very aggressively. So the fact that they have so many registers means they can, remember, retiming moves registers across logic. They can now decide where those registers go. Do they actually go in a logic block, or do they kind of push them all the way into the interconnect halfway between logic blocks? And they can pipeline very deeply. So if they've got something that goes across the chip, and it needs multiple clock cycles, they can do that just by pipelining it in the interconnect without going through any logic blocks and burning up all sorts of registers. They quote numbers in the paper that they get 45% speed up on average on a benchmark suite if they don't redesign the circuits. But if they do redesign them to leverage the fact that they can pipeline more deeply, then they get 92% gain. Now, this includes a process technology change. You know, from 28 nanometers, they go down to 14 nanometers. and they retuned their routing architecture. So this isn't all due to these this registered routing. So, and they don't really separate it out. You can't separate out what is due to what. From the results, my guess is that their registered interconnects may be getting them 30% if they're doing deep pipelining, but that's really a guess from what's in the paper. It doesn't actually directly say. They need to make new CAD tools, so they augment their CAD tools in a couple of ways. So the first thing is they will automatically retime the design several times. So before placement, they basically want to encourage people to very deeply pipeline. And then they want the CAD tools to decide where to put the pipeline registers. So they actually, before placement, do retiming to try to move the registers around to what they think are good places. After placement's done, they do it again. After routing's done, they do it again to try to move the registers to the exact right wires. And then to help end users go even further, they have new CAD tools, basically a new advisor that tells the end user, here's where you should pipeline more, because this architecture is so good at pipelining, or here's a loop, right? So loops become limiting because we talked about how a loop cannot be automatically pipelined, and then a designer has to go in and change the logic. So it can find the loops for you and say, well, this loop is limiting speed. If you can figure out how to do something about it and go faster. Okay, so that's these timing gains. So Michael's got a question of, are these timing gains over Stratix 5? Yeah, so these are timing comparisons to Stratix 5. Okay, so at least I believe it's Stratix 5. I'll go back and recheck the paper to make sure it's not ARIA 10. So if you think I got that one wrong, let me know and I'll go back and check. So okay, so what's happened since Stratix 10? So Stratix 10 is Intel's latest shipping FPGA, but they have announced another one called Agilex, which isn't shipping yet, but they've published, or at least to my knowledge, isn't shipping yet, at least not broadly, but they've published some of how it works. And they've backed off the put a register or a pulse latch on every single routing driver. Basically, I believe what they found is that in Stratix 10, okay, so remember this diagram shows that exactly what hold time they achieve on these pulse latches is going to affect how aggressively they can use them. Can they turn them on one wire feeding another wire? Can they put pulse latches on both of them or not? From results I've seen in Quartus, it appears that they can't turn on two pulse latches on consecutive wires. The hold time isn't good enough on these pulse latches. So they can't really use all the pulse latches they built. They have a lot of flexibility about where do they want to put registers in their CAD flow because they have so many of them, but they can never actually use all of them because it would actually produce hold violations. If they use a register on this routing wire, then they need to have at least a couple of routing wires after that before they use another register. So this routing driver could be a register, but the CAD tools are not going to allow it because it'd be a hold time violation. The other thing that's happened in Agilex is that because wiring resistance keeps increasing, so Agilex is a 10 nanometer chip, and wire resistance for the bulk of the wires, which are on the lower metal layers, keeps going up per unit length. So they're reacting to that by making more short wires. And more short wires, when you have shorter wires, you wind up with more routing drivers. So this is probably going to accentuate this trend. If you have short wires where they don't have much delay, then instead of not being able to use a pulse latch except maybe a second wire, then maybe it would be every third or every fourth. So because of that, they're only about 1/3 of the routing drivers have pulse latches. So the shortest wires don't have them. Okay, so they've done this to reduce area and probably to also reduce delay of the wires that don't use these pulse latches. This is still, though, a lot of registers. So even having 1/3 of your routing drivers capable of being registers is a very large amount of potential pipelining. Okay, so Xilinx Versal also is a bit different. So Xilinx's earlier chips all the registers are, in the logic blocks in the ways that we've seen so far. You basically put the registers after your logic. You have a lookup table and you have a register kind of thing. Okay, so that's inside your logic block. What Xilinx did on their latest chip is they didn't put registers in all the routing wires, but instead of just having the registers essentially at the outputs of a logic block, they put additional registers on all the inputs. Okay, so this LED has, maybe 6 inputs. They basically put optional registers on every one of those inputs. Okay, so they haven't gone as far as Stratix 10 either, but they are getting more register rich, adding in a whole bank of registers on all of the inputs to a logic block as well as the output. This is one of the readings that I've assigned for next week. So they have a whole discussion of why did they do it that way instead of putting it on the routing wires like Stratix 10. So I think that we're done for today. But if anybody wants to hang around and you can guess at what are the pluses and minuses of doing it versus Stratix 10, I'm happy to discuss that now. But with that, I think I'm going to end the lecture. And if you have any questions, I'll hang around. One of the questions on the questionnaire is basically what are some of these differences versus Stratix 10. So you're going to wind up with a chance to discuss that on that summary anyway. By the piano.
Where by the piano? Shoes them now.
They're on the far left.
On the far left of the piano. Do you put them on the shelf or the
Yeah, they're on the shelf with all the stuff. They're on the far left. Okay.